Hey, hello everyone. Hey,
I
Malcolm.
see. Zoom lets me know now that it's being recorded. Is this a new feature?
It is a new feature indeed.
Oh. No stealthy recordings anymore. Oh, there's Aubrey. Hello.
Oh, you're muted, Aubrey?
I like your cap, Marcelo, with the gold.
Yes, excellent. Very good to see you. Very good to see you, Johannes.
Was there a GCC meeting earlier?
Yes.
I couldn't get in. It was just kicking me out.
Oh, boy, that's a pity.
Yeah.
I responded, but I was muted. Hello.
Hey, Johannes.
There we are. Yes, it's going to be a boring seminar if you stay muted.
Yeah.
At least we can make our own conclusions.
Yeah, maybe that's the new way of doing it. Just show the pictures and you will
be quiet for an hour.
You know, Malcolm is a dangerous guy. If he sees a presentation without words, he will fill in for you.
Yeah, I can easily fill in for you. Yes.
Yeah. So Malcolm, you will do the talking, and I will do the slide shifting.
Yeah.
Marcelo, do you remember Malcolm standing up to give a presentation for somebody from Russia who didn't make it for the session?
Yeah, that's exactly the one Marcelo refers to. It's made him forever nervous.
Oh, indeed. I never miss
Don't leave your slot open.
Never do that.
Johannes, do you want to point your camera up a little bit? It's cutting the top of your head
sorry.
off.
Yeah, I have this weird computer with the camera under the screen, so it gives this. So if I'm writing, it looks like.
Oh, that's why we see your fingers. Okay.
Yeah. So I will shift back like this.
No, that's fine. Okay.
I thought you did that because you don't want to appear bald. Isn't it?
Oh. Yeah, it's.
Guys are cruel. You guys are cruel.
No.
It's.
Johannes, I know you for a long time. I think you're looking cool indeed.
Thank you. Yeah, I have stopped with hair.
Yeah.
It's finito.
Wait.
Yeah.
It's okay. On average, we're doing okay, Johannes.
Yeah, I think you and me together. It's some kind of balance.
Okay.
I can grow a beard, but.
So shall we get started? I think there's quite a good number here. Yes, so really very nice to see you again here for the seminar. So it's a pleasure to have Johannes here, and just as the chairman of the GCC, I'd like to just take the opportunity to welcome Johannes Quist, now formally as a new GCC member. So it will be a great pleasure to also see him coming through the door through this fantastic seminar that we're looking forward to hear. Please, Magnus, for the introduction.
Thank you, Marcelo. So my short introduction about Johannes starts 13 years ago. He was then a student in my course in machine elements, and he was interested in the topic, which is not unusual, but not every student is so interested. He also worked for a consultancy. It's a small spin-off company at Chalmers that is driven by students. And that's how we started the first small project together, a development project of a belt scale, an innovative belt scale for aggregate production, more or less. In 2008, we actually moved into discrete element modeling and bought our first EDEM license. And Johannes was the person who commissioned that. And he had at that time very good abilities in CAD modeling, which is one of the foundations and cornerstones to move into DEM. You need the geometry, of course. And Johannes started to model VSI crushers, and they look really cool with irregularly shaped particles and so forth. Very impressive at that time. This was 13 years ago. Johannes did the first breakage modeling in cone crushers later, and in 2012 he made his master thesis on cone crusher modeling using discrete elements. We offered Johannes a PhD position focused on DEM modeling on compressive breakage in compressive machines, such as cone crushers and HPGRs. And he worked on that and presented his PhD in 2017. He has been involved in the MIRA projects P9P and P9Q, also been to many of the Anglo Center projects and workshops, especially in South Africa, worked on the MNC plant in Limpopo, shoveled rocks, not only at the platinum mine, but also in many aggregates production sites. So he's definitely not scared to dig in with his hand and shovel, and which is the foundation to create good results and calibrate the discrete element models. So I want to be short here. Johannes has a position now as business area leader, focusing on DEM simulations at the Fraunhofer Chalmers Center for Industrial Mathematics. So it's a Fraunhofer node. Johannes will explain more, and it's located in the technology park at Chalmers. He has been a bit quiet for a few years, and today we may actually get the explanation why. So with that, I would leave the floor to Johannes.
Thank you very much, Magnus. So let me see if I can share my screen. Okay, so thank you, Marcelo, for the invitation, and also Magnus for that that introduction. It's very interesting to hear those 13 years in such a short list, but yeah, it's been really great, and for me to now present what we've been working on at FCC for the past years it also feels like a lot of fun to show you the development of a new DEM solver. So I won't go into too much detail about FCC, but it's a research institute, and we work both with industry and with academia. So to say, being in the middle of those two. We have, let's see, 3 different departments. So one working a lot with robotics and geometry and motion planning. And then it's the department that I belong to, which is computational and engineering design. And there's a lot of finite element modeling, CFD, and now also DEM since 2017. And we also have a department on systems and data analysis that work a lot with AI and big data and so forth. So this is the small but very strong DEM team at FCC. So I've been working mainly as the project leader, bringing in funds and projects, and also doing a lot of the testing of the software and so forth. But it's the developers, of course, that have sort of developed the whole software, led by Dr. Claes Jareteg, and working with Elin Solberg, Adam Bilock, Franziska Hunger, and we also have a student, Anita Ulrich, that also works in DEM. Okay, so just a brief overview. So DEM, we use that for simulating particle systems, and so far we have been working with quite a lot of different types of materials. Of course, rock materials linking to infrastructure and mining applications, but we also work with plastic granules. We have been working with metal powders for additive manufacturing and so forth. So these different kinds of applications have sort of required different types of modeling approaches, and they provide some different challenges, let's say. And we have developed this solver based on utilizing graphic cards, so GPUs. So the code is written in C++ using the CUDA library. And this provides a very high computational performance on a relatively cheap gaming cards. So it's a pretty good cost performance situation. Okay, so DEM very briefly works essentially like this, that you set up some kind of input for this particle system with geometry and particles and so forth. And then what we need to do is we need to identify all the contacts between all the objects in the system. And then when we have done that, we calculate the forces, and then we update the positions and velocities of this. So that's and then afterwards we can have a look at this and post-process the data. But that's the essential sort of steps. So the key here is to be really, really, really efficient in these main steps. And that's where you get the major performance leverage. So I will start with going into some technical depth, and then we will go into some case examples where we look at some two different cases where we have used the DEM code. But the collision detection, we do that with something called bounding volume hierarchies. So this is the way that we identify which particles are close to a contact. And this is implemented with the GPU as well, making that search very fast to find contacts. And then to calculate the specific overlap between particles to calculate the forces. We do that in a very specific way that's very efficient for polyhedral particles. And historically, a lot of the DEM implementation has been with spherical particles, and then the overlap calculation is very simple. When you move to polyhedral particles, that becomes a bit more complicated to calculate the overlap between triangulations. So Adam Bilock has developed a very efficient algorithm for this. So first, the triangles are filtered by plane equations, and then we compute the intersection nodes. And then we can, from that, compute the properties in terms of the overlap. This implementation, it scales near linearly with particle resolution, meaning that if we increase the number of triangles per particles, it scales near linearly. And the implementation that Adam has done, it enables us to have non-convex particles, so they can have more rock-like shapes, let's say. And this is critical to model rock particles properly. And that's something you will find in literature, that a lot of codes are for only convex particles, and it's a bit more complicated to achieve this property of non-convex particle shapes. And we do the force calculation based on the volume overlap. And I wanted to illustrate this because most other codes, they do it based on the distance in the overlap. But if you look at this image, for instance, these have the same distance in terms of the overlap. But as you can see, when I have oriented this is the same particle oriented in 3 different ways. So the volume will be totally different compared to the distance. So the volume is a better and more accurate way of performing that input to the force contact model. So how do we arrive at different shapes? So what we have done is that we have done 3D scanning of rock shapes. So here you can see 3 different shapes, and they in this image here, they are made up of 100,000 triangles, and that's way too much for us to include in the DEM simulation. So then you can apply an algorithm to decimate the number of triangles. So going to, for instance, 1000. You can see we lost a lot of the detail resolution, but we maintained the general shape. And then down, now I go pretty far down to 60. And that's much fewer triangles. That's something we can simulate, but we remain the general sort of overall shape of the particle with its non-convex features, aspect ratios, and general particle shape. Okay, so that's about the shape. What I had sort of some issues with in my previous DEM modeling life, let's say, was how to efficiently interact with DEM software as an engineer. So we have been working a lot with different interfaces so that it should be streamlined for the engineering context when you actually use DEM for real engineering projects. So we have two main interfaces that you can use to build up the DEM model. So, and the first one, we have configured the core or the Demify core, so you can import it as a regular Python library. So if you're familiar with Python, then you realize that this is very versatile and it's quite easy to get going with. And it's also very, very good for setting up batch simulations if you're doing optimization or evaluating parameters. And because you're essentially accessing each of the sub modules in the DEM core from this Python module, you can do whatever you like. So you can build very advanced DEM setups. Still, maybe this is a bit for the advanced user. So we also have the graphical user interface. And this is built on something called the IPS platform. And this is a software platform that is developed at FCC. So there are 7 or 8 different modules for robot simulations and cable simulations and virtual paint simulations and so forth. So the IPS platform has hundreds of customers and thousands of users. So it's very good for us that we were able to utilize that platform for building the graphical user interface. And we do both we can do both the pre-processing and running the simulation, and then also post-processing inside the IPS. And then what we have recently developed is also a capability that when you run the simulation in the GUI, it will automatically generate a corresponding Python script. And of course, the simulations that if you run it in the Python environment, you can open them and post-process in the GUI. So this is very good because the GUI, usually when you position geometries and you do the sort of basic layout, it goes much quicker when you can directly review what you're doing. But then you have a great power in the script interface for moving forward with batch simulations, for instance. Okay. So I think I made a quick, yeah. So this is the graphical user interface. And I will just quickly go through the different steps to set up the DEM simulation. So basically, you see all of the different parts here in the tree structure. So we start with creating a material. We can define interactions between materials. So for instance, the friction and coefficient of restitution and so forth. And then we can create the DEM part, and then we can use, you can import any number of geometries into the tree, and then you use the ones that you would like to use for a specific part. We can create particle models. In this case, a polyhedral model. We have just drag and drop in a shape like this. We can create particle size distributions of different kinds. And then a generator, that's where we insert the particles into the simulation. So for instance, we have the frequency of insertion here, when it will start and stop, if we will define it by the number of particles or a total mass, for instance. We can also move this generator in the domain, and we can have arbitrary shapes where particles are created. Then we also have something called a destructor, and we can use that for defining if particle enter that domain, they will be removed from the simulation. And now this is a feature that might look like a detail, but it makes a huge difference when you work with this tool as an engineer, because from these building blocks, you can have more than you need for a certain case. And then you can build any number of, let's say, case recipes. So if, for instance, if you're evaluating 3 or 4 different conceptual solutions, you can directly in the same scene build all of those case recipes here and run them. And you can also open up and review those results in the same window simultaneously, which is not possible in other software. And that makes the comparison when you work with the software or much more easier when you compare conceptual solutions, for instance, different flow patterns or what it may be. Okay, and I also want to show something about working with movements and motions. So here I've sped up this video factor of 3. So here we can define something called the waypoint motion. So this excavator bucket moves along this line. And here I've already performed the simulation, and you can see how this bucket moves down into the material and digs through. You can also change the color, of course, using different color schemes. We can have predefined camera positions. Here I'm lowering the transparency just to see what's happening inside the pile. And because of the independency between the definition of motions and the DEM simulation, I can now, for instance, go into this motion and modify it if I want to do a separate new version of this waypoint motion. So now I just lowered one of the waypoints, and then I can run the simulation again and get a second version. So you can work iteratively like this, which is very good from an engineering perspective. Okay, so I just want to mention we have spent quite some time on building an API and a documentation. But let's not go in too much on that. Then I also would like to mention the key importance of calibration. So this is something I worked on previously. We have a methodology on how to work with experiments and simulations to arrive at a calibrated set of contact model parameters. It's important to mention. Now, I would also like to mention that we worked a lot with DEM CFD simulation. And I know some of you have also done that within the GCC. So mainly we have worked together with the pharmaceutical industry. So this is an example of a Wurster coater. So in this simulation, we have 1.5 million spherical particles running on the GPU. And this is used by a large pharmaceutical company on a day-to-day basis in their development and process work. Okay, so I would now like to demonstrate a project that we have been working on for the past 1.5 years. It is not a project within the mining, but it's within infrastructure. And I think it's still sort of relevance because it's rock material and it's a different kind of machinery, but I think you will see some links to minerals processing equipment if you just have some imagination. So I wanted to create a data set where we could validate the DEM model of a roller compaction machine. So we took to a quite ambitious task to do pilot or full scale, but pilot plant experiments. And so here we see the facility where we did this experiment. So we had to position 200 tons of material in the concrete channel without ever driving in it. So that was a challenge. So here in the top right corner, we see the 8 to 90 millimeter material. And then here we have the 0 to 32 millimeter base course aggregates. We also bury these pressure sensors to be able to measure the forces and pressure inside the bed to compare with the simulations. And here is the sort of final bed ready for the experiments. We also utilized a lot of 3D scanning. So we 3D scanned at 6 positions before we started moving across the surface, and then after every second passage with the roller compactor. So we could use that 3D scanning data to extract these sub areas for estimation of deformation. And then from that we can extract, so for what these surface plots shows are the point clouds for 12 passages. And from that we can extract the deformation when we sequentially pass over with the compactor. And there's quite a lot of details regarding the simulation of this system. But we had a master thesis last year, and Johannes Göransson was the student, and he built actually a complete multi-body dynamic solver in Python that he then, with the Demify Python interface, could directly link into. So the complete dynamics of the roller compactor has been modeled and is included in the DEM model. So this includes the stiffness of the rubber buffers and the stiffness of the frame and so forth. Okay, so jumping forward, here's the comparison between the experiment and the simulation. First for static and now for the vibrating case. And here we can see, to the left, we see the static passage. So we just roll over without vibration. And then you see the first and second dynamic passovers. And from the side with some transparency, we can see sort of the movement of the particles below the roller, now with the static pass, and then here with the dynamic pass. And of course, those of you who work with HPGRs should sort of take notice here in terms of this coupling method and so forth. Okay, so when we compare then the pressure response from these ground sensors, this is it's 3 different pressures. It's from the static pass and then 2 first dynamic passes. And the simulated versions, we're quite happy with the amplitude here being very good. But there is some difference in terms of the shape of these. So we have, I think we have some different properties in terms of the internal friction, for instance, that we need to work on. But it's a quite good match, I would say. And then from the simulations, we can also extract new information regarding, for instance, the lateral force direction, which is very interesting for the client we're working with here. And also, I think the response in the granular material and this kind of shape is also an interesting output from the simulations. It has previously been a bit unknown how far down into a bed of material that the roller will actually penetrate. So that's something we can start to investigate also with this kind of model. So summarizing this first case, we have a very good industrial scale validation data set to move forward with publications on. And I would say, like, setting up this experimental campaign, it's based on the knowledge I've acquired through like the surveys done in the minerals processing industry. So this case also shows the versatility of utilizing this Python API in Demify for doing like an advanced system modeling. And we're quite happy with the simulation results so far, but there's more to be done for sure. And the next step we're working on now is to implement this solution the clients to integrate it in the R&D process for developing these roller compactors. Okay, so now a second case example. This is a project we did earlier this year. I cannot disclose the client, but it's in the mining industry. And it concerns the feeding of a recycled cone crusher. And we did this project in collaboration with the Liner Design Service and Rock Team. So before just showing the results from that project, I want to show just the generic situation of feeding a cone crusher. And it's very common that they are fed like this. And in this case, the particles, they hit the spider cap pretty dead on, but the momentum of the large particles causes a splitting action. So the larger particles will end up over here and smaller particles will flow down here. And we also have more material on one side than the other. And this breaks crushers. And as Magnus usually says, all crusher performance optimization starts with proper feeding. And when you look at if you go to a site and look at this, it will be usually a lot of mist and dust, and it's quite difficult to see if you have very good conditions or not. So, and just to showcase this problem even more, we built a simple setup in the lab a few years ago with a laboratory crusher, where we intentionally created the feeding situation with a perfect, let's say close to perfect aligned feed. And then we position the feeder over here to really disturb the crusher. And you can see the difference here in the power draw curves that it really don't like that. And if we plot that power in polar coordinates, we can see actually the shift here in sort of the misalignment. So let's look at this case that we worked on earlier this year. So this is the system setup. So we have a conveyor coming into a head chute, down to a divertigate, into a trouser leg chute, and then into this crusher. And the observed problem was that it was misaligned and segregated in terms of the feed. There was a previous installed solution to aid with the feeding with the rotating feeder, but that had broken down and was not working anymore. So it was basically a pipe like this that had been worn out. So we always start with simulating the current arrangement, because if we cannot replicate the current situation, you shouldn't really go into concept evaluation if you cannot replicate. So that's always the first step. So we worked iteratively to do that, and that might mean that you find geometrical differences on drawings. You might need to 3D scan the actual geometry. Sometimes there will be ledges, like in this case, this ledge had been welded on. Without that, you have a completely different flow behavior. Yeah, so we'll skip ahead a bit here. Basically, we found that this crusher will be, under most circumstances, be have a misaligned feed. So that was the conclusion from the first step. Okay, so we could verify that problem, and we can also see that the wear pattern, it makes sense that it wears on this pipe here. So then the concept solution had already been proposed, consisting of a rock shelf design. And we investigated if that would be a proper solution. And we found that there's a very high risk of blockage. You can see it here with spherical particles, and it's very close to blocking when we simulate with polyhedral particles. So then we move forward to see, could we investigate that concept to make it function? So we simulated a couple of different states, and we separated the distance between these shelves to open up the solution. And the way we did the analysis was that we compartmentalized the crusher into 15 or 16 different domains. And here we can measure the mean size in each of these domains, and also how much mass we have. And for perfect feeding, we want equal mass in each one of those, and we want equal size distribution in all of those. Then we have something to measure and optimize against. So here we can see the 4 different cases that we evaluated in terms of the alignment. And for perfect alignment, we want to have these all of these bins to have the same height. And here we can see the segregation. So in this case, for instance, where we had a smaller size distribution, you can see pretty good evenness. But when we have a wider distribution, we see that coarser particles accumulate over here. And this was a quite interesting case. First, we didn't realize, why do we get large particles in this corner? Is that an anomaly? But when we investigate that further, it seems like it's not an anomaly. Because you can see here progressively that coarser particles end up in this quadrant here. Because looking at the details of this system, when particles move in the head chute, then they move and they bounce against this wall, and then they will have a tendency of going over here. So let's see, you can sort of see that happening here. So now we are into quite fine-grained details of the flow to be able to pick up these kind of differences. We'll jump ahead. So here we color by velocity, and here we color by mass. So if we jump ahead, we'll see. Yeah, it's possible to sit here and track the coarse particles and have a look at where they end up. And of course, they will go a bit everywhere, but they will predominantly move to one certain corner. Looking at this, it sort of matters where the spider cap or the spider arms are located, because it will be a coarse particle can either go to the right or go to the left. So if there's a bias going to the right, we will see that effect in the distribution later. So just to summarize this case, we did it in quite a limited amount of time, and it was a lot of fun, great project overall, with the collaboration with Liner Design Service, the rock team, and of course the site. And we also got this very nice statement from them that this was an extremely well done analysis and helped engineering significantly. And now I sound like a salesperson maybe, but I was of course very happy to receive those comments from the site. It's a different thing working in research projects and then moving into these very sharp industrial cases. Okay, so that was those two cases. I want to show something that is very fresh. This video was, I mean, you can't have a DEM simulation without including at least one video that's done the same morning. So that's I've learned that from Paul Cleary, that's just how you do it. So let's do that. So this is a simulation. This is a polyhedral solver, but it's called a dilated polyhedral solver. So it's a Minkowski sum of a sphere and a polyhedral. And this allows for very, very efficient overlap calculations. It means that for now we can, in this solver, we only use convex particles. But what you see here is actually 1 million convex polyhedral particles with 20 triangles per particle. And it's been running 2.5 seconds for 5 to 6 hours on a quite cheap regular gaming card. So this really is promising in terms of performance, including in this kind of shape. Also, as some final conclusions. I mean, we have been developing this solver and code based on funding we have received from public projects, but also industrial projects. And we're now sort of entering a phase where we would like to also roll out and launch Demify so that others can start using it. And we are open to discussions regarding how to do that and in what way. And I'm just mentioning now that, of course, within the GCC, perhaps the most easy and straightforward would be if we have like a collaboration project, for instance. Then it's very straightforward and we don't have to do very much else than just share the code and so forth with some agreement. But of course, if you would be interested down the line to test Demify, let's have a discussion on that. That would of course be a great fun. And then for industry, so far we have a couple of industrial users. Usually so far it's started with actually consultancy projects and that we do in-depth in development of the specific applications. So we have some niche applications where it's very difficult for an engineer to in the industrial time scale to model advanced systems. So what we've been doing is working directly with the companies to develop those systems, and then from that development project there will be sort of a transfer to more like a normal license agreement. So we work a bit differently, case by case there. Also, I had the intention to include one additional slide, and that's on breakage modeling. So that's something that we have been working with to some degree, but it's really for me the next big thing, and we have had applications for funding on that, and of course that's something that I've been focusing a lot on previously, and that's really where I would like to take Demify next in terms of implementing new types and more efficient rock breakage modeling approaches to really utilize the performance we have here with the non-convex polyhedral shapes and so forth for comminution simulation and comminution machine simulation. Okay, so I think I will actually stop there to leave some room if there are questions.
So thank you very much, Johannes. Very interesting and well-prepared presentation. And as I tried to introduce in my introduction, there is a trace here from early 2008 to 13 years later, today 2021. And it's actually possible to trace the progression over those 13 years. So the floor is open for questions. I think it's possible to unmute and just ask a question.
Yes, I'm already volunteering there. Thanks, Magnus. And yes, Johannes, a fantastic presentation there. And now we finally understood what you were doing, hiding these last few years, that it pulled your hair and everything, but it really turned out to be fantastic. The outcome, very nice. Of course, I would have a couple of comments, but questions, but just one very quick one and another one, which is the contact models you haven't mentioned, but I suppose you're covering everything from non-sticky to sticky materials. Can you just comment on that? And then the second one is also, of course, you mentioned the breakage part, which is I'm quite curious about. What are your thoughts about breakage? Because you can go many different ways, but I was wondering what you were thinking about the approach that you would like to take on that part.
Yeah. So regarding contact models, yeah, I actually skipped that now, but we have, of course, the regular Hertzmindlin models. We have the JKR model, and some different ones for instance, van der Waal forces for powders. But most importantly, the code is written in such a way that it's, I wouldn't say easy, but it's not a big deal for us to implement new contact models as it's implemented right now. So I would presume that our, let's say, library of force models, contact models will grow as the needs sort of needs come in for different kinds of materials and so on. I don't know, Claes, maybe do you want to comment on that? Yeah, Claes, you are the lead developer. Maybe you will say
yeah, not much to add. Yeah, we're pretty agile in the core of the software, with both like sort of straight off algebraic expressions for the forces, but also for different history effects. So carrying history between previous time steps also on the GPU. It's written in fairly functional manner.
Okay, very good. And regarding breakage, I mean, that's could have a separate, complete, of course, presentation on DEM breakage modeling. But I used to use the bonded particle model because it's sort of you set the stage, and then the breakage that will happen when you bond these particles together. But of course, it's not very efficient. And then on the other side, you have let's say fast breakage models where you either replace the particle with a set of daughter fragments, and that's also been a couple of different approaches for that. And then we have the Rocky implementation. I'm not sure about 100% of all the details. I mean, you of course, you, Marcelo, know more of that, who has been working more directly with it. But let's say splitting a polyhedral particle based on some kind of condition. And we have been discussing actually working in a couple of different directions there. I mean, it is kind of interesting to move towards both the very high resolution modeling, small fragments that you bond together in terms of the polyhedrals, building up larger particles, and also working with more like splitting a rock efficiently. The ideas we've had there is to utilize more of the information regarding the contacts on the particles, because the particle will crack, at least in compression, mainly based on the contact points and the number of contact points. Then when you accumulate strain energy on that particle, the amount of cracks and new surface area will be depending on that amount of strain energy. And I think that's something that I would like to include, so that we know where we load each DEM particle. We know from the loading what's the strain energy available, and then we can play with the statistics of failure planes and voids and so forth to introduce the variance in strength of the rocks based on those kind of sort of faults and so on for different rock types. So that's some of the ideas, and then basically have a substructure, for instance, a Voronoi cell structure, and then we'll decide where to crack the particle based on some kind of knowledge about the loading condition. So I'm not sure if you have any comment on that, Marcelo.
No, it's good to hear that it's in your plans, and so
Yeah.
I'll keep an eye open for that. Thanks.
Very good.
So there is a question in the chat from Anton Gladke. I don't know if you see that, Johannes. I can read it. Could you please shortly explain the technical details of the software, the programming language, supporting operating system, Python API?
Yes, sure. So the core itself is written in C++ and CUDA, but that's not something that we expose to the user, let's say. And then in terms of operating systems, we run both in Linux and Windows. And then the Python API, usually we set up a Python interface with, we can use something called, for instance, Anaconda. There is there's a setup process to figure out the dependencies, but it's pretty straightforward. And then it's regular Python code, let's say. Klaus, do you want to say something else on that?
It's a good description. The core is functional C++ 17, and therefore we get Linux and Windows essentially for free between the systems. For Python, we use this library called PyBind, which gives a really fantastic seamless experience between C++ and Python.
There is also a question from Professor Powell. You have raised your hand. If you unmute, Malcolm.
I have indeed. And I gave other people a chance to ask questions, but if you don't get in, so I was wondering which of my 17 questions to ask, but I think I'll go for the one that's maybe the trickiest for you is wear modeling. So I only know one DM code that's implemented at the moment is Rocky, and it's very important in rock handling and transport. So I wondered whether you guys are considering wear modeling.
Yeah, we have been discussing with some companies that needs it, and basically we haven't gotten there yet, let's say, but it's definitely something we have been discussing, and also I guess discussed different approaches to handle that problem. But what I can say is we would like to have a research project with industrial partners on that in the quite near future. I think we would have a bit different approach maybe than Rocky, working with the wear model and how we sort of implement the prediction on how the wear will propagate. But I guess that's natural that solutions can differ.
Is your development pathway going forward that you look for industries with a need to partner with you, and so you start building the tool with them for them to use? Is that because that's what you mentioned? If there's industry interest, you would then take it forward.
Yeah. So let's say we have also seen a niche market, let's say for building advanced setups. For instance, we're working with a process called shot peening, and there we can utilize that we have complete robotics simulation capability in API. So then we link the DEM model, generates the shot peening particles on the end of the robot. Then we can simulate the whole robot path plan, and then we look at where the DEM particle hits the geometry, and then we can estimate the coverage from shot peening. So that's like a complete cycle, modeling that whole machine system. And the company, they are not really interested in doing all of that work. They want to have a basically production-ready simulation tool. So I think that could be also a way that we, from Fraunhofer, can work with DEM in a bit different way than, for instance, a commercial DEM software provider would do, because we can do that research project as a part of sort of the need, the industrial need, or covering that industrial need. And of course, you can employ an industrial PhD student, but usually that can take a quite long time to arrive at the goal. So, yeah.
Good, thanks.
I guess there is still room for a last question if anyone has a question. Otherwise, one of my personal reflections of feed modeling for crushers and maybe similar equipment is how sensitive things are to geometry. And whatever small disturbance you have, it could be, as Johannes showed, a small ledge or an edge. Someone has welded something correctly or incorrectly, but there is a rut or a ridge from the welding. That could, it's surprising how much it can influence. And you saw this pretty high system of chutes. It was 4 times higher than the crusher, and it looked very symmetrical. But of course, there is some inbuilt asymmetric aspects and also some errors somewhere. So I think what we've learned through Johannes' work is it's very important to have accurate geometry. Johannes has worked a lot with laser scanning, been into mills and chutes that are splitting the feed to what is supposed to be identical mills, but of course it will not be identical. So I don't know if you want to comment any on that sensitivity to geometry variations, Johannes.
Yeah, I think it's a very good point, and from my experience, of course, the drawings are sort of the basics, but usually there might be a deviation between the drawings and the real world, or the real situation with engineering change and so forth, maintenance. So that's really something you need to be careful about. I realized that I forgot to mention also, you can build the Demify Python code as something called an FMU. And here I'm running live now from Simulink. So you can build the DEM model and then just import as a block, and then utilize the complete hydraulics and multi-body dynamics, whatever you like in Simulink, So I think this is also something very interesting for instance, I would like to build a HPGR model completely in Simulink and then run it with MFI. And that versatility of the Python code, I think that will be very good for comminution modeling as well, to model geometry and also system dynamics, control loops, and so on in the same system.
Okay, thank you, Johannes. I think we are spot on time. So
very good.
If I could hand over to our GCC chairman, Professor Tavares.
Okay, thanks, Magnus. Thanks, Johannes, for a really enlightening talk there. It really enticed us to be looking closely at your future developments, but it's looking really fantastic and promising. And I think we should, as a group, discuss with you and the team from Fraunhofer on how we can actually engage with you, because it's really a great tool for us. So thanking Johannes again and Magnus for chairing. I definitely thank you all for being here. So next month we're gonna have the last seminar before the, I don't know, the Northern Hemisphere summertime. So in a month's time, there'll be this last seminar before that time. So we will, 2 months will be off and then come back in August, correct? Or September, and kind of, yes, I think it is July, August, yes, we'll be back in September, correct? So thanks all, it's a pleasure to be here with you, and congratulations, Johannes.
Yeah, thank you so much, Marcelo, for the opportunity to present, and yeah, big thanks.